Okay, let's dive right into this explainer and demystify the somewhat abstract world of network protocols. And to do that, we actually aren't going to start with complex code or hardware. Instead, we're going to look at something we all intuitively understand, and that is human communication. It turns out the rules that govern how you and I speak to one another, they are literally the perfect blueprint for understanding how our entire digital world operates.
I mean, really think about it for a second. Right this very moment, there are billions of incredibly diverse devices across the globe. We're talking smartphones, massive servers, laptops, tiny smart home sensors, all trying to connect at the exact same time. If they all just started firing off data without any rules, it would be absolute chaos, just a total digital Tower of Babel. The ultimate solution to that chaos is what we call network protocols. They're these invisible, agreed-upon rules that turn a global mess of data into a perfectly synchronized conversation.
So here is our quick roadmap for today. We are going to cover the basics of communication, why we need rules, encoding and formatting, message size and timing, delivering the message, and finally, how all these protocols work together.
All right, kicking things off with part one, the basics of communication or the elements of connection. Look, whether it's two people talking across a coffee shop or two supercomputers networking across the Atlantic Ocean, every single instance of communication requires three basic elements. First, you need a source, the sender, who actually initiates the message. Second, you need a destination, right, the receiver the message is intended for. And third, you absolutely must have a channel, which is the media that provides the physical path for that communication. Without all three of those things, a conversation simply cannot happen.
Moving right along to part two, why we need rules to make sense of the chaos.
Because just establishing a connection? Yeah, that isn't nearly enough. Imagine trying to read a massive block of jumbled, unformatted text that doesn't have a single drop of punctuation or structure. It's incredibly difficult to comprehend. But if you take that exact same information and properly format it, suddenly it makes perfect sense. Human language relies entirely on grammar and structure to be understood. Well, in the exact same way, network protocols are the crucial grammar rules for digital conversations. Without them, computer data is just meaningless, garbled noise.
Which brings us to part three, encoding and formatting. This is how we actually build the message.
So, it all starts with message encoding. Let's think about human speech again. When I want to share a thought with you, I can't just magically beam it into your brain. I have to encode my thought into physical sound waves that travel through the air. Computers do the exact same thing. They encode digital data into bits, ones and zeros, and then convert those bits into whatever form the medium requires. That might be a pattern of light over fiber optics or electrical impulses over copper wire. And then, when it finally reaches the destination, the receiver just reverses the whole process to decode the information.
Once it's encoded, the message has to be formatted. In networking, we call this encapsulation. It sounds fancy, but it's really just giving the message a highly specific structure. It is exactly like taking a physical letter and putting it inside a properly addressed envelope. The letter itself is your data, but the Postal Service absolutely cannot deliver it without that envelope showing a clearly identified sender and recipient on the outside.
And the technical reality of that digital envelope is what we call an IP packet header. If you look at an IPv6 header, for instance, you've got these large dedicated sections, specifically for the source IP address and the destination IP address. This strict format ensures that as the message travels over the network channel, every single device along the way knows exactly where it came from and exactly where it needs to go.
Let's jump into part four, message size and timing. Think of this as digital etiquette.
Again, think about everyday conversational etiquette. We don't speak to each other in one giant, breathless run-on sentence that lasts for 10 minutes straight. It would totally overwhelm the listener. Well, computers are no different. They have hard limits on the size of what they can process all at once. So networks intentionally break down large files and messages into much smaller, manageable parts. It just makes it so much easier and faster for the receiving device to read, comprehend, and actually process the data. And along with size, we have very strict timing rules. We've got flow control, which manages the transmission rate so the receiver isn't hit with a fire hose of data. We have response timeout, which dictates exactly how long a device will patiently wait for a reply before just deciding, yep, the message was lost. And then there are access methods. Imagine two people awkwardly talking right over each other at a dinner party. In networking, we call that a collision, and it literally corrupts the data. Access methods figure out exactly when a device is allowed to speak, so we avoid that awkward chaos.
Part 5, delivering the message. The question here is, who exactly are you talking to?
Because once a message is sized, timed correctly, and addressed, we basically have three main ways to actually deliver it across a network.
First up is unicast, which is super straightforward one-to-one communication. You're sending a message to one specific device. Then you have multicast, which is one-to-many. Here, you're sending a message to a specific group of devices, but definitely not everyone on the network. And finally, there is broadcast, which is one-to-all, basically shouting your message to every single device on the network. But get this, here's a kind of surprising fact. Broadcasts are heavily used in older IPv4 networks, but they actually aren't even an option in modern IPv6 networks. They are just way too noisy and inefficient for the modern internet, so they got scrapped.
And finally, Part 6, how protocols work together. This is the invisible symphony.
Because the reality is, these protocols actually work as a team, heavily layered right on top of one another. For example, when you load a web page, HTTP, or Hypertext Transfer Protocol, acts as the application interface. It governs how your client interacts with the web server and defines the content format. But HTTP doesn't handle the actual delivery. That job is handed off to TCP, the Transmission Control Protocol, which manages the individual conversation, handles the flow control we talked about, and actually guarantees the delivery of the data. And sitting right beneath that is IP, the Internet Protocol, acting as our global post office to route and deliver the message anywhere in the world.
When you pull all these protocol functions together, you get this incredibly robust, self-correcting system. You have addressing, so everyone knows who is who. You have reliability functions through TCP, so you get guaranteed delivery. And you even have built-in error detection to figure out if data somehow became corrupted while it was traveling over those copper wires or fiber optic cables. These layered functions are exactly what ensures that our digital conversations never break down, even across thousands of miles.
We completely take the internet for granted, don't we? But the next time you tap send on a message, just take a second to appreciate the incredible, invisible symphony of rules firing off right under your thumbs. From the formatting and addressing to the flow control and global routing, it's an astonishing set of protocols working together in milliseconds to connect you to the rest of the world. Thanks for exploring this source material with me today, and keep questioning how your digital world actually works.